Go ahead and sort her out.
Okay. Yeah, we'll probably generate a few comments out online on this one.
Since almost all of physics, but particularly quantum and modern classical physics, involves complex variables, I thought we'd spend at least one lecture, but more like two, on some neat ways to look at complex variable theory that I'm pretty sure you haven't seen before, looking at this Unit 1. Chapter 10 is what we're really doing now. And the whole idea of answering the questions here, what good are complex quantities or variables? Well, I've got about 16 answers to that we'll cover in the next, certainly this lecture we'll get to somewhere in this neighborhood, and then the more erudite parts of complex variable theory will come in the next lecture. But there's a starting point here that's really elementary. We've already mentioned a couple of things about the exponential and the number e, and I'd like to do more of that right away to get started here. And it involves, the most elementary description of e involves banking. So that's what we'll do first. And we'll catch up on all the screens here eventually, but I'll use the first two few things here on these slides. Now, the usual collection of links that apply to this, and in particular, since we're going to be using phasors in Unit 4 to describe a lot, this is a good introduction. This is an old website that you might want to take a look at. It's real fun, a lot of fun things there. In any case, this all starts off here by asking a question that is fairly elementary, and as I say, try to follow all the screens on this since we have to compare things and make a good story here. But what I'm asking you to answer, and I'm just curious how many people know the answer to the question, what sort of interest would you get in modern banking at 100%? I'm imagining, spent some time in Brazil, so I remember this, and also in Israel. There were quite long times in both of those countries where they had 100% interest. And that's fun to play with, especially if you're a victim of it. And idea, of course, is that if you put $1 into the bank at 100%, it's pretty obvious what you get at the end of the year. And the formula for that is just 1 plus rate of interest times time, times the initial capital, initial principal. That is the correct term for banking. So that is one type of interest. The next type of interest that came along about that time that people could obtain was a compound interest with a half period and a 6-month period. And so that involves an interest at the half period that is multiplying the what you started with. So you have 2 of these 1 plus rate times time, but now the time is a half, and we're same principle, $1 coming in. And as you can see, you get quite a bit more by compounding. Well, 25 cents more if you're $1, but if it was $1 million, you've got a lot coming in there, 250,000. So that's a a situation that is part of our ancient banking system. Now, if you're going to do it in a trimester, if you're going to do it 3 times, so you have 3 factors on a principle like that, well, you get even more. Now you get 37 cents added to what was originally just $2 in an ordinary single banking period. And you might think, if you were so inclined to be greedy as a banker, that if you kept doing this, you might be able to get infinite interest. That is, this could just keep growing each time you compound it. If I did 4 times, 5 times, maybe every month, maybe every year. The truth is, it's not the case. And so your cigar sags and your greed goes away if you're the banker thinking that you could cause this to happen. Now, the more frequently that you do this, and let's just go ahead on both of these screens here with the situation that I will be describing. I'll do it on the upper screen there as well, and here. So the basic idea is, if you were to do it here, you have squared, cube, and 4th power now. 237 is what we got with cube, but 4th is 244. You're not adding it very much. You only add 7 cents to the yearly product. And then if you get really fancy and you decide that you want to do it 12 times monthly, or 52 times weekly, or daily 365 times, or hourly, okay, you see, you get a number here which I think you recognize. You're approaching E dollars. Okay, so that's a neat way to describe what does E give you to somebody that's just in finance, say. That's infinite. That is what you get by compounding infinitely. So that's what I'd like to look at here. I'd like to look at not just compounding 365 times. Let's go 1,000 times, 10,000 times, 100,000. It's kind of interesting to see how this develops. And when we get all done with this, we're almost to E here. All I need is to turn that into an 8, and I've got 10-figure E here. And this is my favorite calculator. I got this thing in 1980, and it's very faithful. It's capable of doing basic. I mean, I don't know of any calculator, even ones you could put on the phone with apps, that's as good as this one. So that's really quite, I'm amazed that the thing still works, but it works better than any other calculator that I know of. Anyway, I just took a picture of it here, and you see the numbers, it's remarkable, 2.7, 18, 28, 18, 28. That's 10 figures. Looks like it's a repeating decimal, doesn't it? But it's not. Next number is 4, okay? So, that's one thing I wanted to show you here. This is with 1 billion products. Actually, more than 1 billion products to get this. We're not quite there yet with this. So you see, that's one of the things, just to get a feeling for this number and how it behaves in terms of building things. Well, I find that very useful to talk about. But we've got to improve the ways we calculate this. This is not fun. I'm going to have to multiply something 1 billion times. I'm going to be here a while. So the question is, can we improve the computational efficiency? And the answer is yes. By simply writing that formula, that binomial formula, out as a binomial, and then taking the number n to a very large number. That is, imagine it's going above the 1 billion. Okay? And when you do that, you get a very big simplification for this thing, which I'll show here in just a minute. But let me bring the rest of the screens along here. There's the formula there that I want to make sure that everyone has in their memory. permanent memory, everyone should be aware of this little series right here. So basically what we've done here is, first of all, make use of the fact of the factorial is some approaches some high power as we go more and more products of it of the number n that we're talking about here. And if that's the case, we can just leave n out of the formula entirely. The only thing that's left is the rate and the time, and then our summation our summation variable. So this is a heck of a lot easier way to calculate E. You see, I only have to do a few steps of arithmetic, and I'm getting the accuracy roughly this level here, and it gets better and better as you go along there. So just to make a connection between doing something by an iterative operator, which is what our quantum mechanics does. We apply operators over and over again. Most of those operators are expressed as exponentials of some generator. So that's the main reason in modern physics for learning about this exponential behavior. Okay, as I said, I'd like to follow along with these things, so I'm going to just leave this one for the time being in that position, and this one I'll advance similarly, and then we'll pick up in a minute here. But anyway, the idea of a power series is important. In the power series that come with complex variables, that's nothing I'm going to talk. The Lorentz series is not something we'll get in this lecture for sure. That's very much the last topic. It will be in lecture 13, the unlucky election. That's where things get a little hairy. But in any case, the idea that every function can be, just a single variable can be expanded just with positive powers, that's all we're going to talk about in this lecture right here. But the using negative powers, that's the Lorentz series, that's important too, and we'll see the physical need for that as well as mathematical. In any case, the rate of change is then something you can calculate very easily from a power series. You just go down and use a derivative formula for each of the powers, and you get a velocity change in position. And we've done this before when we were talking about the phasor in the oscillator, but this is for any function of time that we've got here. Next comes a change in velocity, which is the acceleration. And then NASA gets on this game here. And as I say, this is a proper term. The change of acceleration is jerk, and we'll use J of t for that, like we did before. This was the third part of our discussion of the oscillator phase space, and all of that. And then we're being silly like NASA. The change of jerk is inauguration, and so forth. Perhaps you could go one more step here and have change of inauguration as revolution. I hope we don't go through that with our country, but it could happen. Now, the Maclaurin or Taylor power series is written this way, and it should be noted that your sophomore physics students, if you're TAing right now, elementary, this is the good old UP1 formula for what you do with things that are in constant gravity, like the problem on a cycloid that you have that we see for next Wednesday. But again, if you want to make an exponential function, if you want to make e to the t, you just make all of those initial conditions equal to 1. Right? That does it. There's the exponential power series. So the whole idea of a power series being a precise thing is really part of our physics beyond the things that are analytic. That is, the part of a physics where you use computers to get things, but you approximate just about anything with a power series under certain conditions, and those are things that we'll talk about a little bit later here. So let's jump ahead here and take a graphical look at what a power series does for us. If you just look at the exponential, that's this red curve right here coming up. You see the red line is the exponential, which we've already had a problem we said we had to graph that thing in some way. But here what I'm trying to show is what you get if you just take the first part of that. If you just take 1 plus t, okay, there's 1, and then plus t, that's a straight line. So there's a first approximation to the exponential right there. And it's pretty good for about 3 pixels, okay? And then you start seeing it's falling away, the line falls away. It's just a tangent line, is all you're getting from that. But then you just tack in there a quadratic parabola in addition to that. And now look how much more you can go on that curve and get within a pixel of the red exponential line, and so forth. The cubic comes next here, but it's divided by 6. But in any case, it serves up to about this point right here. Now it's a little bit hard to see how this thing is going to be doing for really higher terms. How well does it do? This is not the curve to pick on for that. The curve to pick on for that is going to be a different curve entirely. The sine curve and the cosine curve. So I want you to see this. This is something that you need a calculator. You need modern equipment in order to do this. And a lot of textbooks, I would say virtually all of them, haven't caught up to show this. This is really beautiful. Now I'm just going to look at the cosine first here. The cosine being an even function. Everything on this side is the same as everything on this side. You put a mirror here. And this is a similar thing, except everything on this side is negative on what's on that side. So these are all odd powers in this series. But this series right here, half of the exponential series is sitting right there. And you can see that it's got a 1 and then nothing for t, because that's odd. But then it's got a parabola right here. So when we talk about making a potential in a pendulum, there's a good potential. If only I put a minus sign on the whole thing, turn it over, I have a pretty good parabola for, from there to there. And then you see the purple line deviates. And then I go to the next one, which is the fourth power. The fourth power, there's a fourth power. You guys are working in solid state physics. That's one of the model potentials for phase transitions. We've already talked a little bit about what happens if you add a linear to a parabola, but this is a way you get it with even functions only. Okay, you can see it takes us down to about here and then peels off. All right, and so forth. As we go and put on the sixth power, okay, we manage to get down to here before it peels off. And then we put on 8 power. We go to here and before it peels off. Okay? So each one of the peel off distances is the same forever. That's pretty cool. That's a real aha right there. And it's not mentioned anywhere in any books that I have read. I discovered this by playing with a calculator. Okay? And that's something you should do with every kind of function that you're going to be working with. Because perturbation theory is essentially a power series. And it is good for being a power series, and it fails because of a power series. So this fails. You see, every one of these is a failure at some point. Complete failure. I mean, it's gone, right? Kind of weird, right? It goes along and obeys in like the 9th, or the 12th, or the 13th, or 15th, and boom. Right? That's just the way it is. That's what mathematics is doing for us, okay? Now, that all aside, that's cool. That's a neat thing that I want to talk about. But it would not be good if we only talked about interest rates that are real. If you're like the people at Deutsche Bank, Trump's favorite bank, or the Cyprus money laundering pit you use imaginary interest. Okay? And when you use imaginary interest, things to oscillate. This is a way to make the counts go up and down. And you can see that by putting an I here for our rate, okay, and expanding it out. And what do you get? What you get is what we already looked at. You get now a cosine plus I times a sine. It's the Euler theorem, Euler-Moivre. Okay? That's cool. All right? Well, that's what we're going to be working with. This is really important. This is our wave function in quantum mechanics, basically. A fundamental wave function would be something like that. We talked a little bit about that. So here's a cosine series, here's the sine series. Add them up with a little I there, and you've got this situation. Okay? Now, we have already mentioned that is a nice way to display a phasor. That is a real axis and an imaginary axis. We talked about it as the position, and then in units of omega, the velocity. That's real versus imaginary. Very nice. Okay, that's a good thing to have in your mind. I'm going to come back to this picture. But I want to point out, before we get too far here, and I think it's time to go ahead and advance this one up to this point as well, just so we can be talking about the same thing. And I want to make sure that you do not forget about the other side, the real side of this. I'm going to take this one ahead here. Do not forget hyperbolic sine and cosh, okay? That is really a key, a part of what we're going to be doing, well, throughout this course. So they're very different worlds, but they're connected. And I would say, if you're going to be teaching somebody mathematics, you start with this one. This one doesn't involve imaginary numbers. You can stick those in now and get this one very easily. But we do things backwards. And not only that, but the stuff on the back of your notebook, that diagram that's on the back, and I think I've got one sitting on a table there just so I can point it out. I'm going to show that next, but it's a trigonometry lesson. I'm going to do that one, okay? So, I want you to realize that there's more to this story than just the imaginary part, just the circle part, okay? There's the hyperbolic part, where you track the area subtended as a major variable. So I'm going to take this one up to the next thing here, and then I want you to be aware and get some time to play with this function. So I'm going to take this one ahead now, just to have a sketch of it, and then I want to actually try to run this one right here. And I think TC has set this up so that it should work fairly nicely. So what I have here is the ability to raise the little area. That is, as I raise the angle, we don't measure the angle as degrees. We measure it as area. That red area there is sigma, and the sort of dull gray and green area, this other area, going up to hyperbola, is another variable entirely, a variable that goes forever. This one just goes around the corner and finally finishes up with 2 pi, or I should say pi, the area of that whole circle here is a unit circle. But all of the functions, sine, tangent, secant of the angle sigma, that turns out to be the stellar aberration angle on this diagram. That's the transverse way to measure the speed of light that's coming transverse to your direction of travel. You'll see it tip over by angle sigma. Exactly. The direct way to measure a speed is with the Doppler shift, which in the row here, the area of this hyperbola is the logarithm of the Doppler shift. So this is the part of connecting relativity and quantum mechanics and basic geometry, basic trigonometry. So if you're going to teach somebody trigonometry, this is a real playground. Construct everything here with a ruler and compass very easily. A couple of steps for every point that's on this graph here, and you see the values of the functions. Cosine is the same as a sec, hypersec, you see, and a regular sec is the same as a cosh, a hyperbolic cosh. Numbers are exactly the same. This is using sigma, this is using rho. Tangent, same as the sine hyperbolic, and the sine is the same as the tangent hyperbolic. And then these two play with each other, cotangent and cosecant. Okay, so this is really neat. I mean, the idea of these things being the same, you see, is key to stuff we're going to be doing later, but stuff you're going to be doing your whole life if you stay in this business. Okay. All right. So I just wanted to make sure that you had a chance to see that and play with it on your own, just to get a feeling for what is coming here. Now I'm going to go ahead on this one. And some stuff that I've already said a number of times in this class is the phase business is part of that. But here's, I would say, the first thing that answers the question, what good are complex exponentials? That's the main thing driving a complex variable series, so it's a good question. And automatic trigonometry. You're in an exam and you've forgotten what cosine of a plus b is, or sine of a plus b. You get both of them just by factoring e to the I a plus b to e to the I a and e to the I b, and then separating them. The real part gives you that formula. The imaginary part gives you that formula. So there's one real use of complex variables that you didn't have if you didn't know about complex variables. Okay? Bingo. If you want to get the sine laws or the cosine laws, these are things that involve these things as vectors. It's a two-dimensional space, real and imaginary. So take advantage of that, the sum and difference. That's how we get started building relativity out of two waves. And we'll do that at the end of the course. But you can go ahead and study that before we get there. It's really a beautiful thing. And we've already mentioned this, the phasor, okay? Tracking position and velocity as a clock. That is, all the waves are made out of any number of clocks, basically an infinite number of clocks, but you only have to do a few of them in order to show most of the wave behavior that you find in quantum mechanics. And you have to write that thing either in a polar form or a Cartesian form, and you go back and forth between those two forms in order to make all of this stuff work. So I'm going to take this thing up and start with this slide right there, and we might as well do the similar thing with the one down at the end of it. I think I'm just going to leave this one with this picture for now, the one with showing the power series. Okay, so that's all well and good, but it's also, and this is another answer to the what's this guy good for, rotation, dot, and cross products lose their mystery. That's neat. Rotations, first of all. How do you rotate a complex vector? You have a vector sitting there, you want to rotate it, you put this guy in front of it. And these things can get, so you can put it in back if you want. But for two-dimensional things, there's the answer. Well, the alternative to that is to get out all the fancy vector and matrix analysis. This is a rotation operator right here, okay? And it's got in it two components that we already have, real and imaginary. There's a real part, there's the imaginary part. So this is a matrix it's doing, and this is a counterclockwise positive rotation with a sign up in this corner. We talked about the other one, the minus sign was down here, and then we put the minus sign in the cosine, got a reflection. That we've already talked about, but this is just one very simple operation that you see. And while you're at it, you can also see the various components of the things. You can see how they, here's the vector that we had originally, there's the rotated vector right there. Okay, so I want to make it a point that this thing is an operator as well as just a number. But it's an operator acting on a complex number. Now the other thing is that this provides, as I say, a demystification of the cross product as well as the dot product. And this is a funny thing that we're going to be doing later on in order to make this three-dimensional, using the spinners or the quaternions or whatever you want to call those funny things that are a generalization of complex numbers. So just be aware that that's on the horizon. We'll be doing that in Unit 4. But right now I'm just going to do A star. What's that mean? A star means that you conjugate it. That means you take the i's and turn them to minus i's, wherever they might be in this parentheses. Okay, I leave this one alone. It doesn't have a star on it, but this one does. Okay, and that's kind of looking like A product B. Later on, that will take some significance. Right now, it's just a symbol for turning I to minus I, and then you put it together in its real and imaginary parts. The real part is the dot product. The imaginary part is a particular component of the cross product. And that component is involves a component in something out of the screen, a big Z, out of the screen, perpendicular to X and Y, but it's just a number. That's all it is. It's not a vector like a cross product is in a three-dimensional sense. Nevertheless, there's your AXBY minus AYBX. Okay, that's pretty cool. And then write it in polar form if you'd like to. Okay, and you see right away that the sign pops up in the product of the curl thing. The dot product, the cosine pops up of the difference in the angles between them. So A dot B plus I times A cross B. But it's only a number, not it's the big Z component of a vector that you're used to. Okay, so that's cool. That's making some sense out of some things that I think anyone finds confusing on their first exposure to the cross product and even the dot product. Okay, and taking it back again, this is a trigonometric identity that comes tumbling out of this. Okay, now this is where it gets a little bit hairy, and this is where something that I have not seen anywhere. I just thought this up and started doing it because we had a computer that could plot fields. This is where we're going to get into vector calculus, and we're going to be doing vector field potential theory. We're going to be doing source-free field theory. That's what we're going to be doing, but we're going to be doing it elegantly and easily. But we have to do some hairy stuff before we get to that. So at this point, I'm going to go ahead on, let's see if I'm doing that right. Yeah, that's where I want to be. Let's take this step by step. The first thing that we have to do here is apply a chain rule, a funny kind of chain rule. This is a little bit bizarre, but we have this transformation between writing X and Y, just the real and imaginary parts, and the, shall we say, functions that we can make out of the X and the Y. We can either make X plus IY or we can make its conjugate, X minus IY. So the hairy thing about this is we consider these as though they're independent variables with every bit of the independence that X and Y have. We just treat those guys as, well, they're part of the crew now, okay? They're allowed to be in our society, okay? And so when we talk about a derivative of f with respect to the whole number, z, it's a complex number, and this f here is itself complex, well, we got to do a chain sum here, a chain derivative sum here with the partials. We have to do a partial of x with respect to z times partial of f with respect to x, and then a y with respect to z and f with respect to y. But we already know what the conversions are for these variables, real and imaginary parts, and we can simply write the ddz as, well, and this is the mystery part of this thing, as 1/2 of the partial derivative with respect to x minus 1/2 of I times the partial with respect to y. So there is an expression for ddz, and you take the conjugate of that, and you just change the minus to plus. So this is what we have here as the derivatives that we'll be playing with in the physics of the complex variables in fields. So that's the next step here. And what you discover by doing this is that the real part of this derivative gives you a two-dimensional divergence. There it is. That's the real part of it. Just go and separate out everything that has no I, and then put as things that do have I on this side, and lo and behold, you have a cross product of a Laplacian operator, but it's only in 2 dimensions. And this thing right here is a number, just like this one. Divergence is a sum of partial derivative, x with respect to x, y with respect to y. But this one is the backwards, it's the y with respect to x, minus the x with respect to y. There's your curl derivative, your rotational derivative is here, your flux derivative is here. So flux is real, rotation's got this imaginary part. Okay, so that's what we're going to play with for today. It's just the differential. Get into the integrals and all that maybe at the end, but for now, I just want to see if we can understand this. And while we're at it, we're going to do a job that we really need for this mechanics class, and that is to build coordinate systems of some variety. We're going to have them given to us for free by just playing with the fields that we get by studying the divergence and the curl of F will stand for force. Probably a physicist force, but really we're going to be dealing with a mathematician's force. We're going to now, for today, when we talk about a gradient, there's not going to be any minus sign on that to give the force. We're going to be talking about the force to hold things. That's what mathematicians did. And the mathematicians are responsible for potential theory, so they get to make a choice here. Okay, simplify, not have so many minuses. Okay, so that's what's going to happen here. So be aware of that little sign change here. And what we do is we are going to invent source-free vector fields that have both zero divergence and zero curl. Now, how do you do that? Well, you take any function of z, you conjugate it, that is, change all the i's into minus i's that you find in that function, so that you have 2 stars here, one for the actual outside of the function and one for the independent variable, which is z star now. And if you do that, you will have something that's only a function of z star and not a function of z. The derivative of the starred function with respect to z will be identically 0. Now that's easy to arrange. And when we do that, we'll get some beautiful field and a coordinate system to go with it. So this is where we invent various kinds of weird coordinate systems that we'll be using for mechanics later on. But we do it fairly easily. Now, the first example that I want to do, and I've got a program here that unfortunately you can't play with because it's in the old Macintosh thing. We can lend you a Mac and you can play with it that way, but I'm going to go ahead and turn that screen aside for the moment now, and I'm going to run the screen way down there on the same as this one right here. Okay, so bottom row here, which you guys can read over there, and we'll read this one on this side of the room, is that I have here a field that I'm going to make just by taking the variable z. Okay, what's it look like if I just have a first power of z and then some constant multiplier? I'll make that 1 for the most part here. So here's what it looks like. F star z star then will be, I'm assuming A is real, or I don't have to assume that, it could easily be not. But I'm going to get z star, x minus iy. You see, what a dull field that is. That isn't very interesting, is it? Well, we'll see. We'll see. But whatever it is, it's not a function of z. So it has 0 z derivative. And that means it has 0 divergence, and it has 0 curl. Now divergence, you remember, that's the thing that measures how much of a source, scalar source, there is. This measures how much of a vector source there is, and we're going to have none of that and none of that. All the sources are going to be outside of the screen, so to speak. Okay, in our playground, we're not going to have any sources. Okay, right, just as long as that's clear. And you can see that's true here. I go through and try the thing out, and I get 0, and I take the divergence of the field that this is giving me, which is ax, and then minus ay. That cancels, so we're out of here. This one right here, it turns out to be 0 as well. Okay, so some of the names for this, by the way, you see this in Jackson, I think, is the divergence-free laminar. Divergence-free and curl-free. Laminar stands for curl-free. Okay, well, I guess I should probably start generating some of these fields for you here. And to do that, I need to run this old computer here. It has this little thing where you choose a particular force function. And I'm choosing kz. You figure, that's pretty dull. How could that be interesting? But let's go ahead here, and one of the things I'm going to do is make sure that this thing is in black mode. So I'm going to have a black background on this screen in the center here. Let's go ahead and plot. What we'll do is we'll plot the actual vector field by clicking here. And I hope it will work for us. So I've got a black background, and there we go. Okay? Now, what I'm going to do, just for the heck of it, is I'm going to be drawing. I mean, first of all, notice what this field represents. It represents a quadrupole somewhere outside. Really, a quadrupole at infinity is the way a mathematician would say it. But basically, there's some source down here that's letting all this stuff come up, and there's a source up here that's got it going the other direction, coming down, and then there's a sink down in Fort Smith and another one up in Springdale that's taking all these vectors in. If that was the way you wanted to imagine this thing, it's maybe water flowing. But it could also be electric field. That means it could be a bunch of negative charges in Fort Smith and Springdale, and positive charges way up in the air there and way down inside the earth. And they're giving us this field at this particular location. Right? So that's the story that this particular one is telling. Okay? And this is once again showing that everywhere in here, there are no sources. There are no sources to produce more of those little arrows, and there are no pinwheel sources, rotors to stir it up and make them turn the corner unduly. Okay? So there you are. Just f of z equals z gives us this. Okay? Now you might go back and ask, and this is certainly possible, anytime you want to play with this thing, I stop this thing and ask, what does it look like if I just take a constant? F of z equal a constant number. All right? Let's plot that. Well, there it is. The constant happened to be real, so it's just all a bunch of vectors with real value 1, or whatever coefficients you set, and those coefficients are available to be set And we are working on having this available on the web, but it's not trivial. Okay, and so it's taking a little bit of time. But there's the uniform constant field that you get. We won't do much with that for a while. I'm going to come back and get this one going here. And what it is that I want to show are the potentials that go with this. That is, what does this kind of field give us? And we've got a source-free field theory, but I want to look at both the scalar potential and the vector potential. Get some feeling for the vector potential, because we probably already have a pretty good feeling for the scalar potential, but the vector potential, that's weird. And we're going to need that to really understand some mechanics later on, particularly if it's in electromagnetism mechanics. So, any divergent free laminar field is the gradient of both a scalar potential, and you could just stop right there and tell the whole story with that, but it's also the curl of a vector potential. It's both. This field is both. That's cool. I mean, sort of get, it's a twofer. You get two for the price of one. Okay? This is the complex potential you're going to get. Okay? And you basically just have to integrate the sucker in order to get that. Or here, this guy right here, complex conjugate. Okay? If you were to play with this one, this would have a z star derivative. It would look like that. So basically what we're going to do is we're going to look at this force and see what happens when you integrate this. Okay? And you say, well, that's really hard. I've got to do a compensated Hahn rule, and we've got to pull that off. Well, you don't need to even think about this being as a complex variable. You just integrate it as though it was a real variable. And that's kind of neat. So, first of all, here's our first thing. What we want to do is get this thing as we want to get a potential whose derivative gives this field. That means we have to integrate this complex f with respect to z, okay? And what I get then is the integral of az dz, that's 1/2 az squared, okay? Just ordinary calculus, no fancy stuff. Here we just treat it as though it was a real variable. X plus iy squared is what it is, and I expand that. And the real part is the scalar potential, the vector potential is the imaginary part. Okay? Now, let's go ahead and get this thing working again up here. And this is now going to be f of z equal az. So let's go ahead and show that. And now the first thing I'm going to show here, and I'm doing this just sort of to be funny, but there is an equipotential. There's another one. There's another one. It just does a numerical integration here to get that. And then there's another one right there. There's something weird going on there, but that's just the way that this particular field is. If I come here, I can start right there and make another hyperbola. This is a hyperbola. This is a hyperbola. I get another one. Anywhere I click, I get whatever equipotential line goes through the point that I click. Okay, so here we're getting a whole bunch of equipotentials. So how's the calculus on this screen jiving with this particular thing? Well, you see, this guy we haven't looked at yet, but these guys we know and love. That's a hyperbola. That thing being a constant is a hyperbola. Either a hyperbola coming down or coming up, or left and right. Okay? Now, this program is set so that I can remember all the stuff that I've clicked up here. All these equipotential lines will remain through a stop. and I will just go here and say, I would like to plot instead the vector field line. Now you can do both at once, but that's a little fast for what we're doing here. So let's go ahead and plot the thing again, and now click, say, right where this arrow is here. You see this arrow going that way? There's a streamline that that arrow belongs to. There's a streamline that that arrow belongs to. There's another one with that arrow and that arrow. So everywhere I go here and click, I get flow lines. Color them blue. It's kind of like blue water. Okay? There's one that's kind of a sharp, very sharp hyperbola. I can go right on the edge here and get even sharper. Okay? And then I can keep doing this. You see, what I'm doing is producing a quadrupolar infinity potential. I'm producing a BEC trap. This is a trap, a part of a trapping mechanism that you would add in some experiments. And wherever you start, it follows the arrows. You see, everywhere that curve is, tangent to that is an arrow representing the vector potential. You see, the vector potential is a completely independent description of this field. Wherever I click, and I'm doing it at the, so that the arrows start the thing up, and you see all of those arrows are close to, and some are exactly tangent to if they happen to go through that neighborhood. Okay? So there's the XY part of this field. It's the vector. Isn't that cool? It's a nice way to take care of the function f of z equals z. And there you have a perfectly orthogonal, curvilinear, hyperbolic, I guess, coordinate system that we can use for some mechanics later on. This is where it comes from, basically from field theory, simple field theory. Okay, let me see if I'll get one more good one in there just for the sake of, because I want to plot this thing as a function of x and y and look at it in 3D. Look at the actual potential heights, both for this and this. And we'll do that with some other things shortly here. Okay. There's a picture right there. Now the thing about having no curl and no divergence is that I have a conservative and integrable function here. And that means that I will get the same answer as I measure how much my potential, either one of them, changes by going from here, say along that path, to there. But as you know, if this is a conservative field, that's what it means to be, have your partial derivatives commute and all of that, to be integrable, okay, to get a unique result from doing an integral, is that I'll get the same difference by following that path, or that path, or that path, or one that goes to Springdale and comes all the way back and lands here. All of those will give me the same drop or rise going from here to there. So this is a path-independent field. All right? Because you can write it as potential, a unique potential. Okay? All right. And that's both vector and scalar at the same time. All right? Powerful. All right? As I say, bonus. Every time we pick another function of something, in this case z to the first power, okay, I get another coordinate system. A GCC coordinate system, but it's really OCC, and we'll see it has to be OCC. Automatically OCC. All right. Okay, we're getting there. Now, at this point, I've got to use the right-hand screen so you can read what's going on down there, as well as what's going on near where I'm standing. But let's go and take a look at what this means. And these are what are called Riemann-Cauchy derivative relations. I call them half and half, and you'll see why. complex potential contains the scalar field, describes the field entirely, or if I want to use a vector potential, describes the field entirely. Okay? This derivative has either a gradient of a potential, you can write it like that, or it is a curl of the vector potential, and you can write it like that. This is queer stuff, in the sense that what I'm doing here, I'm measuring this complex potential, and we have to turn it to z in order to make it do a particular thing. If I just plotted f of z without plotting f of z star, I would get something that would, had lots of sources. But this one is well managed, and I'm interested here now in taking that z derivative of this thing, that's this thing right here, and there's the z star derivative, the one with a plus sign in it. Remember the actual derivative with respect to z's got a minus sign on the imaginary, this one's plus sign, so I attach that, work on this, and I get here the gradient of it, so that's what this amounts to, is a gradient. This is the x component, that's the y component of the gradient. And then here, this thing has an x and a y component too, but it's cattywampus, and it's giving us a curl of A. But they're equal. Each one of these gives the same result. And that's what the half is trying to tell you. You can take this formula literally and do half of this one and half of that one, get the whole field. And here's where I noticed the mathematician definition. F equal plus the gradient. Okay, I don't want minus signs if I don't have to. The physicist definition just makes for trouble. Okay, so here's the deal. There's a complex potential. It's got a real and imaginary part. You could either take the gradient of this and go home and forget about the vector, or if you're a hydrodynamicist, you can screw this one. Hell with it. I don't gradients anywhere I know of. I'm working with fluids. I need to work the vector potential, the streaming potential. Okay, or if I'm in magnetism doing magnetostriction, I just work with this one. But they're both available. They're both available. They will give the same result. It doesn't matter which one you use. You can give 1/3 of one and 2/3 of the other if you want. Okay? Now these half and half results, the fact that this works, the fact that I get the same answer with the partial derivative of x with respect to the real part as a partial with respect to y of the imaginary part, and then the same story down here, okay, the fact that that works is result as written as Riemann-Cauchy derivative relations. Now we'll talk more about how those come about. But if the x derivative of the real part is equal to the y derivative of the imaginary part, and the y derivative of the real part is equal to minus the x derivative of the imaginary part, if that's true, Riemann-Cauchy conditions are satisfied. And this is what you learn in complex variables here, right? Well, here's why. You see it in a physical way. Why that is. Okay, so that's the beginning of the Riemann-Cauchy story right there. And all of this is, part of the story. Okay? Now, what Riemann-Cauchy conditions are really testing is analyticity. What is that? What's analytic and what's not? And too many people come away from complex variable course saying, well, analytic just means it's finite. It's not analytic when it's got poles or done something weird. Okay? That is basically wrong. It's right, but it doesn't tell you what's really going on. So we have to answer this question. What does analytic mean? These fields that are so special, they have no sources. What is it about them that is true? So we just go back and look again at what we've just done here. We've got this transformation between the x and the y, and then we've got the z and the z star as competing choices of independent variables. And then we just look carefully again at the derivative of f with respect to z and the derivative of f with respect to z star, and see how that comes out. Okay, so here's a chain rule, and then we go ahead and we evaluate the partial of x with respect to z. The partial of this with respect to z is 1/2. So I plunk that down. I do that again with a partial y with respect to z. Well, I've got to put some 1 over 2i on that one, so you get a minus, okay, in that expression for the derivative with respect to z. But the z star derivative has got a plus sign. I put red with positive stuff here, and blue for the things that come out the way you usually do with a negative sign, okay, this one in particular, okay. So, the criteria for a field function to be analytic function, it must not be a function of z star. That would be, if I decide I want to use f of z. We used f star of z star to start with just to make things, no minus signs show up on where they aren't welcome. So, right here, by demanding that be 0, I then have that be 0 and that be 0, and those are the Riemann-Cauchy conditions right there. You just derive them from the derivative expression. Okay? But that's not the end of the story. What about the other world? The other world involves the function star. Okay? This is the derivative of f with respect to z right here. Okay? That's the thing that's maybe we wouldn't want to be 0 if we were playing with f of z instead of f of z star. But okay, be aware, there's an anti-Riemann-Cauchy condition. Okay? If you're working with f of z star, or f star of z star, okay, either one, okay, then it's df dz, this would be 0. And having that be 0 gives me these. Okay? That's kind of the opposite of these. You've got a minus sign in this one, and a plus sign on that one. All right? So be aware you can play both sides of the street here if you know what you're doing. A lot of symmetry. Okay? Now, here's a really pedestrian way to say what's analytic. Okay? For example, is the function 2x plus iy analytic function of z? Or z star? Well, no, it's both. And that makes it not analytic. Okay? We test it. We test it by writing out, we got 2x and 4y. I'm writing out from these variables the x, z plus z star over 2, the y, that's minus I, z minus z star, okay, over 2, well, over 2i if you took the minus sign off. So I'm going to stick that in for that, and I'm going to stick that in for that. I can stick that right in there, okay? And when you do that, that's what you get, but it looks like a mess. We gotta sort this thing out. It's 3z minus 1 z star. This is not an analytic function of either one. Okay, that's the definition of analyticity. Has to be a function of one of them, or the other, but not both. Okay, so it doesn't have to go to infinity to be non-analytic. So the answer is no. It's a function of both. So not analytic for either. Okay? What about x squared plus y squared? No. That's the absolute value squared. It has both z and z star in it. That's what you do to get probabilities out of quantum mechanics, right? Psi star psi. Okay? It's not an analytic function of either. Okay? How about this little guy here? Yes. I'll put that in, and it's back what we have. Z squared. That's that's a part of a potential. We'll talk about source. All right. Okay, enough of that. Let's take a look at some more complicated situations, and also look carefully at the integrals, okay, that count circulation, and then the imaginary part that counts the flux. So now we're going to do Stokes and Gauss laws all together, all at once. Okay. So what we're talking about is what we have been talking about, an integral of a function of z, say between 2 points, and gathering from that both the scalar potential, that's this thing, difference, and this difference here is taking us as well the vector potential difference. That's important too. They're both equally important. It's just that most of us are brought up on this side and don't get a chance to see really what that one is telling you in the mathematical sense. Okay, so and I'm not being honest here in keeping the screen down there in line, I'm sorry. But that is a little hard for me to do. I keep getting lost. There's the Riemann-Cauchy thing, and now we're doing a look at an integral, how integrals work. Okay, so let's just go ahead and expand that the integral, and here it is drawn out. Now this is a little weird. I have a choice here. Can I just work with f of z, or should I go back and work with s star z star, which is what we started this lecture with? Well, I like to do that because things come out nicely, as we saw with the fields. So here I'm taking the integral of this thing with respect to z of the whole thing starred twice to make it back unstarred. Okay, here I put down the dz, okay, and then I've got this star with a dx plus I dy. So what I got to do is I got to collect real and imaginary parts of that combination. Well, I pull up both the fx dx and the fy dy. So right away in the real part, I get a good old-fashioned force interval. Force times distance. What could be more classical mechanics? But if we're working with hydrodynamics, and that's part of classical mechanics that no one teaches me anymore, here I want this one too. I want the cross product of the force with a particular value of the, well, it's kind of the curl. If I interchange the dot to cross, what I'm interested in is an integral of the force over a cross product of the differential with the big Z, the unit vector coming out of the screen. Well, that turns out to be a flux integral right there. This is a circulation integral. That's cool. That's really neat. So that sort of finishes our discussion of what good are complex variables. All right. Here's this one right here that's measuring f dot, the path that we're following that goes with the field, f dot dr, and doing it from one point to another to get a difference in potential. So we're kind of looking at the circulation integral here, if you will. This one is a little bit screwy because you've got a dr dez, but that is cross product. That's the imaginary part of, and imagine a surface that comes out of the screen here that this stuff is all fluxing through on that picture up on the field view there. So this is measuring the projection across the path. That is the flux through an imaginary surface that comes out of the screen unit height or whatever it takes to make the mathematics work. Okay, so here's a chance to look at these potentials in 3D. This is something you really should do with a textbook or the notes. If you have it on your screen, you can do the thing where you look at this one with your right eye and this one with your left eye by simply putting your nose here and then backing off and getting it in focus. So what we're going to be doing is we're going to be showing those pictures. I want to show the picture of what the scalar potential looks like and give you a feeling there, I think, for what is coming. So what I have to do is go to the computer here, this very old program, and I'm just going to get out of this particular one. But I'm going to leave its memory there. I'm not going to erase. You can do that right here and start over with some other potential. But right now I want to plot over here the thing as a, I'm going to plot the XY grid, and I'm going to plot the lines that go with it and see if I can do it. And I'm going to do it, first of all, in mono 3D. We'll go to cross-eye 3D later. That's what I believe this is. And that way you can actually look at it with that in 3D. But here you can see that what we've got for the scalar potential is a saddle. Now remember, all of this stuff is coming from f of z equals z, right? And we're looking at the integral of that, which is z squared. So this is a quadratic function. Okay? And there are the flow lines, the blue lines, flowing down the hill, presumably. But that would be if you were a physicist and took this thing literally. Actually, with what we've done, which we don't have that minus sign, the holding force is what's being plotted, so it's actually flowing uphill and then up there. But that saddle, pretty obvious that is a saddle. And as I swing it into this position here, you begin to see the potential lines sort of lining up until finally they look like straight lines. It takes me a little bit more turning of the thing to get to that point. But you can see the equipotentials are equal height. There's that, there's that, there's that, and that. They're all straight lines when looked at down, say, the y-axis or the x-axis. I'll turn it back to a more 3D-like view. Okay, so that's what that one looks like. But what about the other guy, the imaginary part, the flux potential? What about the vector potential? That needs some look at. Just real quickly here. And it is quite different. If I plot that one, well, it's a saddle too, but it's all twisted and it's kind of in a different orientation. All right? But there you go. That's what the vector potential A looks like as a function of x and y in a 3D plot. Okay? All right. Well, the next example we're going to do here is, and let's get it started setting it up here. I'm going to stop this right here. And I'm going to say I would like to look at not z, actually a times z, but a was a unit. I would like to look at a thing that has a, let's see if I've got it here. Yes, I'm going to be looking, this was a quadrupole at infinity. I would like to look at a really simple one, a monopole at 0. Okay, so that's our next talk here. Next thing we're going to talk. And when you click on a new function, you have a choice. You can say, cancel my action, undo changes. What I want to do, and I don't want to save the curve. I just want to erase that memory and go ahead and make the changes that I'm going to do, whatever the potential is. So here is the vector field showing the flow from a monopole, a positive monopole. With a negative sign, those arrows would all point in. Now at this point you might say, well, now you've picked a potential that definitely has some flux. It may not have any curl, but that thing looks like it's got some divergence. I mean, it's diverging, isn't it? Well, no, it isn't. Only at, and now our singularity, the point of non-analytic behavior, is dead center. That's the only point on here that's non-analytic, and I mean going all the way to infinity. Because it's dying, and it will be 0 by the time it gets to infinity, even be 0 in Springdale. So when I go now and start plotting, and I think I'm set to do vectors, I'm just going to be making radii. This is a pretty simple GCC. This is called polar coordinates. And I'm just doing the angle variable right now. Okay? So let's do a bunch of angle variables here. And I'm doing them. It doesn't matter where you click, you'll get both sides of the thing. And I'll do a couple more. And then we'll do the scalar potential on top of that. But we also have to do the calculus that goes with this thing, and then look at it in 3D to really understand it. We're only looking at it in 2D plane at the moment. So I'll have a guy going down the axis, and one next to the axis, and maybe another one. And maybe I need something here just to make it sort of nice looking. Okay? So there are all the flux lines lined up with the arrow vectors. And now I'm going to stop this guy, and I'm going to go ahead here and say, I want to plot the scalar potential. So back to scalar we go. And I'll keep all the stuff that I have there, but I'll just go ahead here and click anywhere. And what do I get? A bunch of circles. So just like I said, 1 over z for a force, I should say, scalar potential log z, but for the force, 1 over z, actually a over z, a constant over z. And I'm going to go ahead and make it have potentials even out here on the edge. Okay, so I'm being a little careless here with the spacing, but then I'm not trying to actually make it equal potential, equal spaced. All right? Okay, so there's our curve. Now let's go back and ask for a plot of the potential versus the coordinates in 3D. Okay, so there'll be a big z-axis now, and then the potential will be along that. So let's plot that, see what we get. Isn't that beautiful? Okay, 1 over z, what could it be, right? Well, the integral is a logarithm. Those are a bunch of logarithmic curves rotated there. Now to see that, I'll put it forward on this side as well. See, here I'm going over coordinate systems a little bit more here. So Jacobian, okay, is interesting. I forgot to discuss that. Let's go ahead and skip ahead here and look at the monopole, the unit monopole field. Okay, unit charge, force field, pick your constant, anything you want. When I integrate 1 over z, it's a logarithm. Okay? Real part and the imaginary part of that are really key. This thing that we are going to be looking at 3D, okay, has logarithm as far as the scalars goes, but it's just a constant that depends on the angle as far as those blue lines go. So they're making a helix, helicoid actually. This is making a morning glory or logarithmic, whatever. Remember how the logarithm sticks to the axis? So it's so sharp there, right? Okay, and it's in all directions. This is in all directions, right? So there is a really beautiful view. Now, looking at these in 3D, it's probably a little hard for us to do that in the classroom. But if you stick around, well, I'll set the thing up for cross-eye, and you can look at this thing in 3D. It's kind of neat. But you can see what it is without that. It's pretty obvious what we've got here, and I can tip the thing up here so you really see it edge on, and you see the equal potential lines are all in a plane of some height. So that's what we're dealing with here. Now, this is a notice that probably we're done now, and sure enough, I'm looking at the clock, and we are at the UA limit for a 3-hour, I guess it is, class. So I do have to stop, but we've still got to do some stuff with this to understand it, because the vector potential is weird. It's a helicoid. And it's only 1 power of z does this. Okay. All right. Any questions? It's fun stuff. I'm trying to make things that are usually pretty dry a little bit wet.